This is T2 day 26, max min circles and squares. So continuing on with the work we've been doing with maximum and minimums, just getting more and more interesting. But before we do that, we're going to investigate a little bit about the idea of local maximum and minimum versus global maximum and minimum. We've mentioned this in class occasionally, but haven't spent a lot of time or gone into a lot of depth on this. So let me just talk about it just for a second. Consider that you're going on a long bike ride, and a local min or a local max is when you're at the top of a hill or when you're at the bottom of a trough. So you're riding along, you're going on a 20-mile bike ride. In that bike ride, there's going to be plenty of times you get to the top of a hill. When you get to the top of the hill, we're going to call that a maximum. Now the top of that hill that you just got to may or may not be the highest altitude that you will attain during your entire bike ride. There's going to be some little hills you go up and then you go back down. There's going to be some bigger hills you go up and then you get back down. And it may be that you live on the top of a mountain, so when you've gone to take your bike ride, you start at the top of a mountain, go down for a long time, and then go up a little bit and get to the top of a small hill. Go down, get up to the top of a small hill. The tops of all of those small hills, each one is considered to be a local maximum. The global maximum is over the course of that entire bike ride. When were you at the highest altitude? That's your global maximum. And the same thing pertains to minimums. Then you get to the bottom of a valley, it's called a local minimum. You get to the bottom of another valley, it's a local minimum. Now it may be that one of those local minimums is the lowest that you're going to get all day, or it may be that you ride your bike from that mountaintop home down to sea level, and at the end of the day you end up at the coast, and that's the lowest you're going to get to overall, and that's your global minimum. It could also be that you rode somewhere and you were below sea level, and so that the bottom of that small dip was both a local minimum and it was your overall lowest of the day. It was your global minimum. So local max, anytime we get to the top of a hill. Local min, anytime we get to the bottom of a valley. The global max or min is over the course of your entire trip, the entire period of time that you're looking at. What was the highest you got to is your global max. Over the course of your entire trip, the lowest you got to was your global minimum. Okay, so now let's go ahead and talk about this problem. If I want to find the maximum value on this interval from -5 to 5, if I know I want to find a max or a min, I know I'm going to be taking a derivative. So f prime at x is equal to 6x squared plus 6x minus 36. I'm going to set that equal to 0. 0 equals 6x squared plus 6x minus 36. I'm going to divide each side by 6, and I have x squared plus x minus 6, and that factors nicely. We've got x plus 3, x minus 2, so x equals -3, or x equals 2. So we'll make our sign chart just like always. Nothing new so far. Key values on here are -3 and 2. These are x values coming from our derivative. And because we had nice factors, I'm going to put my x plus 3 on here. I'm going to put my x minus 2 on here. I have a 0 at -3. Negative, positive. I have a 0 at 2, negative, positive. Negative times a negative is positive. Negative, positive times positive is positive. So we're headed uphill, we're headed downhill, we're headed uphill. This is a maximum, and this is a minimum. So we would have been just done before. What's our maximum, what's our minimum? We have a max at -3, we have a min at 2. And that's great, but what is our, so this would be a local maximum, this is a local minimum, and this may be our global maximum, this may be our global minimum, but we don't know how high we're coming up on this hill. We don't know how low we're going down at the end of, before we started up this uphill. So we're going to come back to our interval of -5 to 5. So from -5 to 5, I know that at 5, I'm going to be up pretty high. At -5, I'm going to be down lower than I was at -3, but how high? Well, what we'll do is we'll come back to our original function and we'll say, well, what is f at -5? What is f at -3, at 2, and at 5? So plugging in these values into our original equation, f at -5 is 11. Right. Yep. At -3, it's 87. F at 2 is -38. And f at 5 is 151. So while this is a local maximum, and this is a local minimum, this point at 5, 151, is higher than -3, 87. So our global maximum is here. So if I'm looking at my local max, it is -3, 87. But my global max is at 5, 151. My local min is here at 2, -38. But if I look at this point out at -5, at -5 I was at a height of 11. This is still lower at my local min than I am out at this end value. So my global min is the same as my local min at 2, -38. So a local min can be the same as our global min, same for the maxes, but it could be that while we have a top of the hill at -3 and a height of 87, when I continued on my bike ride, I went up to the top of this hill, I went down a ways, I continued on uphill, 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 and when I got to an x value of 5, I was a height of 151, and while it's not the top of a hill, this is going to continue up, but I'm only looking from x values of -5 to 5. The highest that I will be between -5 and 5 is that height of 151. I've pasted in a graph of f at x, and in looking at the graph of f at x, we see we do have a top of the hill, a local max, at -3, and it's a height of 87. But my overall maximum value for this entire graph is out here when x is 5. I'm up at a height of 151, so my global max is x equals 5, y equals 151. My local max is at -387. For my minimums, I have a local min, I have a bottom of the trough at 2, -38. My overall lowest point for this entire graph is that same point at 2, -38. So that's the contrast of local max and local max min and global max min. So on our next page, we have the maximum area of circles and squares. Okay, so this is another max-min problem, following along from all of those Farmer Brown problems. This one's a bit more complex. We've got a bunch of stuff to consider, but the process is the same. So let's start with, we have 2,000 feet of fencing, and it's used to create two circular enclosures. Circle 1 must contain at least 1,200 pi square feet, and circle 2 must contain at least 600 pi square feet. So let's label this as being circle number 1. This is circle number 2, and circle number 1 must have an area that is greater than or equal to 1,200 pi square feet. Circle 2 must contain at least 600 pi square feet, so its area must be greater than or equal to 600 pi square feet. What is the maximum possible area? So we're maximizing area. Maximum possible area that can be contained in both circles. So if I want my total area, that's going to be made up of the area of circle 1 plus the area of circle 2. And this is what I'm maximizing. And it suggests here that we let x equal the radius of circle 1 and let y equal the radius of circle 2. Okay, so I know that the area of a circle is pi r squared. So my total area is going to be the area of circle 1 is pi x squared. The area of circle 2 is pi y squared. Well, the same as we've had the problem before, that we have too many variables, we again have too many variables. So I'm going to say, all right, well, I've got 2,000 square feet of fence. I know that the circumference of a circle is 2 pi r. If I'm going to make both circles, I've got 2,000 feet of fence. That's going to be the circumference of the first circle, that's equals 2 pi x, and the circumference of the second circle, 2 pi y. Divide each side by 2, and I have 1,000 equals pi x plus pi y. Well, my goal here is to get rid of one of my variables. I just as soon get rid of the y. You could get rid of either one you want. But let's solve for the y here. And I have 1,000 minus pi x equals pi y, or y equals 1,000 minus pi x divided by pi. So, important equation, I'm going to put it in a box so I can come back and find it. So that's my substitution equation. I'm going to come back now to the main part of my problem. What is it I'm trying to maximize? And I'm going to substitute for that y. I have a equals pi x squared plus pi, and now this whole thing, 1,000 minus pi x all over pi that I'm going to be squaring. Well, I need to take a derivative, and this looks pretty ugly, so yeah, there's not much we can do about it, except I think maybe inside these parentheses, let's distribute this pi. That might make it just a little bit easier. So a equals pi x squared plus pi, 1,000 over pi, minus x squared. We did this problem the other day, just as a review problem, just practicing. So we want to take a derivative. We have a prime equals 2 pi x plus 2 pi, everything that's in the parentheses, it's my u value, minus x to the first power times -1, chain rule. So I'm going to put this negative over here. I've got a prime equals 2 pi x minus 2 pi times this parentheses. Distributing that, I have a prime equals 2 pi x minus, multiplying that, 2,000 plus 2 pi x, or a prime equals 4 pi x minus 2,000. Another important equation. So, as always, we're going to set this equal to 0. Our 4 pi x minus 2,000 equals 0. 4 pi x equals 2,000. And we have x equals 2,000 over 4 pi, or 500 over pi, which is approximately 159.2. Okay, so going ahead, as we always do with our sign chart, we've got our x values. We're looking at our a prime. Key value is this. I'm going to put 159 because it's just a number we can get our heads around, far more than 500 over pi. So 159.2. This is a linear equation, goes uphill. So these are negative, 0, positive, downhill, uphill, minimum. Are we looking for a minimum? No, we're looking for a maximum. So we're stuck. That's a minimum. So we got to figure out what we're going to do here. Clearly, that's not the right answer. That's going to give us our minimum area. Our farmer building these pens wants a maximum area. So we're going to come back over here to our restrictions. And we're told that our area of our first circle has to be greater than 1,200 pi. Well, that tells us that, switch colors here, tells us that pi x squared has to be greater than 1,200 pi. And pi y squared has to be greater than or equal to 600 pi. Coming back to this one, that's x squared is greater than or equal to, dividing by each side by pi, greater than or equal to 1,200. X is greater than or equal to the square root of 1,200. I'm not going to take the plus or minus because a negative for pi, for an x value doesn't make any sense. So x is greater than or equal to about 34.6. So, all right, well, x needs to be bigger than 34.6. That's important. If I solve this for y, though, pi y squared is greater than 600 pi, y squared is greater than or equal to 600, y is greater than or equal to the square root of 600. Well, we don't have this in terms of y. We've got it in terms of x. So instead of finding out what the restriction is on y, let's come back over to our substitution equation, plug that in here, and find out, well, what is that going to mean for x? So since y is 1,000 minus pi x over pi, that's got to be greater than or equal to the square root of 600. Multiplying each side by pi, we have 1,000 minus pi x is greater than or equal to pi square root of 600. And subtracting the 1,000, negative pi x is greater than or equal to pi root 600 minus 1,000. Divide by a negative pi, and x is less than or equal to pi root 600 minus 1,000, all over negative pi. Note that I've changed the direction of the inequality arrows because I've divided by a negative. So I've got x is less than or equal to, let's see, this is going to be 1,000 minus pi root 600. Yeah, because I just don't like having that negative in the negative. I got rid of that, multiplied top and bottom by the -1 over pi, which is about 293.8. So, and this is an x. So x, come back here and use this bright blue, x is bigger than 34.6 and less than 293.8. And both of those are less than or equal to, greater than or equal to. So if I come back over here and say, all right, well, my restrictions on x has to be bigger than 34.9 and less than 293.8. What I'm looking to maximize is my area. I want to maximize my area. Well, right here, I have an area equation that's just in terms of x. So I'm going to put this in my y1 of my calculator. So I've got to be careful of parentheses as I'm typing it in. But if I put this equation in my y1 on my graphing calculator, I can then evaluate I don't know what that is. I can evaluate A at 34.9. I can evaluate A at 293.8. And if I wanted to, I can evaluate 159, A at 159.2, which I know is going to be the minimum. But I find that the A at 34.9 is 256.6. My A at 293 is 273. Oops, that's not a point, that's comma, 614. This is 273.063. And this is 159,245. So the largest of these is this 273,063 square feet. When x is 293, and our y value, I'll have to put it in here, our y value equals 1,000 minus pi x over pi, y is equal to 24.5 feet. So I can either use this equation that's all in terms of x, or I could have found my y value when x is 34.9, my y value when x is 293, and then use the simpler equation. But in any case, I want to know which combination of x and y is going to give me the largest area. And these restrictions, one of these is going to be higher than the other. As it turns out, the area when x is 293.8 is higher than the area when x is 34.9. So my global maximum, my maximum from 34.9 up to 293 is when x is 293.8, and that area is 273,063 square feet. Hope this helps. These are big problems. Let me actually, before I turn this off, let me just back this up a little bit and look at what all we did here. We had our picture with these restrictions that we didn't use until the end, but what is it that I'm maximizing? Substituted, so I just had a single variable. Had to use this circumference, the fact that I had 2,000 feet of fence, to get a substitution equation. So substituted, took a derivative, set it equal to 0, found a value, did a sign chart, but was disappointed when I found that my key value was a minimum instead of a maximum. Then I came back over and took care of these restrictions. This restriction was already in terms of x. This restriction was in terms of y. So I needed to substitute again to have this restriction also in terms of x, then once I put the restrictions on my number line, I had to find out which area is higher at which end. So we will do plenty of these problems as practice. These are going to be some of the tricky ones, with these restrictions being the most challenging. So again, we'll talk about this plenty in class, but I hope this helps.